Hello again, YouTube. I am here again with the IR transmitter and receiver. So last time we had the photo transistor just getting this signal, and it was coming through with a nice 10 kilohertz frequency, except one of our problems was it was a very slopey signal, meaning it just didn't look right. You know, data is supposed to have perfect edges, up, down, perfect step functions, they're called. So the way we can get rid of that is by getting rid of our ambient noise, as I touched on a little earlier. And that's at a frequency of 120 hertz, so that means we want a high pass filter. So I did some calculations, and I got, so this is what we want to do. So we have, here, I'll draw it out on my whiteboard. So here we have a high pass filter, out resistor, capacitor. The reason this works is because a capacitor acts as a short circuit at high frequencies. And we have 1/2 pi tau, tau being our time constant, RC. So we have 1/2 pi, and this is our characteristic frequency. So also known as the 3 dB frequency. Since we're working with a high pass filter, this will be the lower 3 dB frequency. Now the 3 dB frequency is also known as the break frequency. So you have it here. So this is a typical Bode plot. This is our gain, our mid-band gain. Here is our a lower 3 dB. So this will be 1/2 pi tau. So that's 3 dBs from our mid-band gain. So what I'm doing in this circuit here, sorry for the lighting, turn this on. What I'm doing in this circuit here, see, I added another photo transistor in parallel. That's in order to make it so you have more range. Remember, they're in parallel. It looks like they're in series, but they're actually in parallel on the breadboard. So here we have our capacitor and our resistors, and these were carefully chosen. I'll show you how they were chosen. I wanted a gain that was anywhere greater than 1. I chose a gain of 10. So if you recall, you have you're not inverting op amp. I'm sorry, you're inverting op amp. So that's your inverting op amp. Remember, inverting, you have your voltage source going to your negative terminal of your op amp. So whenever that happens, whenever you have the negative voltage source going to the negative terminal of your operational amplifier, it's going to make your gain negative. That's why it's called inverting. It inverts your signal. And if you had, this is just a little background, if you had R1 and R1, so they're both the same values, that's going to give you a phase shift of 180 degrees. This is the AC source in this sense. So you're moving this over like so. Okay? Now this looks very familiar just familiarize yourself from the high pass that I just showed you to an operational amplifier, and we can do the same in one stage. So we have our VN, and we're just going to do the same thing. Here is a high pass filter that also amplifies your signal. So I wanted a gain of 10, so this will be 10R1. So I chose a frequency of 10 kilohertz from my transmitter. We want to get rid of 120 hertz, the ambient light. So we design around that. 10 kilohertz equal to 1 over 2 pi times our capacitor C plus, so we have a resistor coming in from the previous stage. If you look here, you can see we have this resistor going to ground from the emitter of our phototransistor. So we have 10 kilohertz is equal to 1 over 2 pi times C, and then whatever the capacitor sees. So around the capacitor. So if we have a capacitor here, and this is R1, R2, this is separate. This is just basics here. So say we wanted to find the 3 dB frequency of this little circuit. So this is V in, this is V out, and it's whatever the capacitor sees. So tau is whatever the capacitor sees, so it's R1 in parallel with R2. So if we go back to our circuit, we have 1 over 2 pi times C times whatever the capacitor sees. So the capacitor sees R1 in parallel with R1 plus 10R1. So now you choose an arbitrary value for R1. So let's say 1K. So we have, so that math comes out to. So as you can see, I worked through the math. I worked with a 9 kilohertz. I don't care, I'll let through everything past 9 kilohertz. Because, you know, my signal that I'm transmitting is 10 kilohertz. I want to make sure not to cut through that. And nothing's ideal, so you always want to give yourself space for error. So we have 1 over 2 pi. There's our time constant for this pup. It works through, this comes 916. C is equal to 2 pi times 9k times 916. C is equal to 20 times 10 times 9, 10 to the 9. And I implement that into the circuit here. Anyways, I put 2 capacitors at the base of the phototransistor. And you can see they're in parallel because I only had 10 nanofarad caps. So I put 2 in parallel, and that adds them up. Opposite of resistors, remember that. So I want to let you know that that's a LM714 operational amplifier. I'm running it with 9 volts. Oh, let me show you. I almost forgot. Let me show you the frequency of the signal, and you saw a little of it in the last episode. And if you go back, you can see how curved the signal is, and that's very undesirable. So let's look at this new signal. Yeah, see, perfect square wave now. You can see it's still 10.2 kilohertz. That's good, consistent. But as I move further away, I dampen the signal. So let's improve on that. And that's what I will be doing in the next few episodes.